So this is our afternoon session. So we have 2 talks this afternoon, followed by a discussion where I've heard many controversial questions floating. So just keep those in mind for the actual discussion. We may have some adversarial examples in the audience, and that's very welcomed. Great. So our next talk for today, it's going to be Zack Ulissi coming from Meta AI, who's going to, and formerly CMU, who is going to be talking about, I think, some things that are also going to be quite related to previous themes we've seen.
Super. Thanks for the invite, and thanks for organizing this. This is great. And also one of the super fun things about the Bay Area is to have all these people in one place interested in similar things. Like I know a lot of you are quite local, so it's really fun. So I noticed that the title and the abstract on the schedule for mine was blank on the official one, so I took it on myself to do whatever I wanted for this. And it's also great following Aditi and Rafa and everyone else talking about these different potentials, so I tried to skip where I can and talk about things that might be a little different. So Aditi also told me I wasn't allowed to spend the whole time talking about and publicizing where I am, but I figured one slide was fair, so no pun intended. So FAIR is fundamental AI research. For those of you who haven't interacted with us, it's about 300 to 500 researchers in blue sky AI research. Mostly things are open and reproducible, so it gives us a lot of leeway to open science and open data set as much as we can as possible. That's been really fun coming from an academic position. A couple of the things that we've done on the open side, so you all have probably seen things like Llama 123. Those are open LLMs that anyone can use. There's also been a lot of work in vision, so things like segment anything. You can show it a picture that is quite out of distribution, and it will pick out all the different objects. And then there's been a bunch of generative things like make a scene and make a video. There's a large effort in embodied AI, which is getting AI agents inside of robots, so things that can go around the house or help you with tasks. And then the final area that's gotten a lot of traction, especially in the past 6 months or a year or so, are things in the speech area. So I don't know if any of you saw, but just this week or last week, No Language Left Behind was published in Nature. So that was a big splash of trying to do translation across many of the world's languages outside of just English, Mandarin, German, French, the things that are obviously showing up in the open data sets. We obviously have access to world-class compute resources for data set and model development. So on the simulation side, that's really nice because it's not just scaling on the GPUs for model training, but we can also build data sets really fast. I'm talking to a bunch of people at Berkeley and LBL, so you also have a world-class resource, lucky you. When I was at Carnegie Mellon, I didn't have a machine like Perlmutter right next door. And the chemistry team is about 15 people. Mostly the open work has been on catalysis and direct air capture. We've had a couple of data sets that I'll talk about. More recently, someone made the connection that actually Meta does care about materials for headsets, AR, VR displays, and things like that. So we've also been helping on some of those applications too. But all of the open science stuff is catalysis and direct air capture. Okay, on the climate side, without going into a ton of details, we've had a couple of different data sets and projects. One is on coming up with different metal organic frameworks for, let's see if this works, for direct air capture. That was OpenDAC. We released that last fall. That's been quite fun. That was in collaboration with Georgia Tech. The other area that we've invested heavily in is electrochemistry and catalyst discovery. So things like taking CO2 and then turning it into fuels or small molecules that we need as building blocks for the chemical industry. And the same sort of work that goes for catalysis to take CO2 and water and turn it into fuels. You could also use in a fuel cell to go backwards, take hydrogen and oxygen and recombine in a fuel cell. So I'm not going to go into a ton of detail just based on the talks we've had and the discussion. I think this is more of a machine learning fundamental audience. But if you have any questions on how this fits into catalysis or how we're using these things, feel free to chat afterwards and I can go into more detail. So in order to make this field move as fast as possible, we've worked really hard to try and make this a community problem. And so there is a website, opencatalyst.org, that's been up for about 4 years now. We run a leaderboard. Anyone in the world can submit to this thing. It's an automated system. You make predictions on the test set and you upload, and then the things get posted automatically. We aren't gating anything, just anyone who has a submission, we're happy to host. We also do things like run challenges at NeurIPS. So the past 3 years, there's been an Open Catalyst challenge. There's another test split every year, another tweak on the challenge where we try and collect more contributions from the community and help machine learning people who want to help in climate science make an impact on chemistry. Really core to this has been the training data sets. So a couple of people have already mentioned the Open Catalyst data sets, tested, Rafa did as well. We've released 2 big ones in the catalysis space and 1 big one in direct air capture. So we call these OC20 and OC22. And like I said, one of the really nice things about being at Meta is we can run on idle data centers. So these were each things that took order hundreds of millions of CPU hours, not core hours, CPU hours in order to run. And that's only possible because when the servers are not serving cat images to you on Facebook, they're running our simulations doing chemistry. It's a really cool opportunity. I think these are some of the largest in the world. Other people are building really, really large simulation data sets as well. So things are moving quickly. But just to give a sense of scale, as Rafa mentioned, we're in the order hundreds of millions of structures that we try and train on. And really importantly, because we want this to be a community challenge and we want everyone to benchmark, all of this is open sourced as permissively as possible, Creative Commons. You can do whatever you want with it, commercial, non-commercial. If there's anything that you think is missing or anything that makes the data set hard to use, send us an email or post on the discussion board, and we're happy to help you use it. And maybe just as importantly for the machine learning community, it's not just enough to dump all your data online and say, we wish someone solved this problem. You also have to make this a challenge where you're sure everything is apples to apples. So in addition to the data, we have a series of train and various types of validation and test splits that are indicative of different challenges in catalysis. And so if you want to submit to our leaderboard, you have to make a prediction on a test set that we've never released, just the inputs. And that's how we make sure that everything is fair when it goes up on the website. And again, everyone is usually operating in best faith and doing the right thing. But anyone who's developed these models knows how easy it is to accidentally shuffle something and start doing inference on test inadvertently. And so these are important things if you really want to make sure that the community is doing the right thing. So again, without going too much into detail on fancy graph neural network models, because a lot of people have already talked about this, I just want to point out that in the past 4 years, we've seen a huge number of submissions to the leaderboard, and there's been a ton of progress in making these things work better. So some of this is scaling up in terms of the representations. So there were a lot of models that were working on bonds and angles. And so one of the core things about GemNet was including dihedrals and higher order interactions. That was a cool thing that that model sort of brought to the field. Tess also mentioned that there were these interesting convolutions that were developed by Larry Zitnik on our team, basically taking computer vision ideas and convolution operations there and try to make them more scalable when we try and do these really interesting message passing systems. And then ESCN is an example where we basically tried to do that in a way that we didn't lose the equivariance. And so that's where the little E is. It's an equivariant spherical channel network model. The best model right now, currently top of the leaderboard, is Equiformer V2, which Tess talked about. Tess talked a little bit about one of the main things that made Equiformer V2 different from Equiformer, and that was the special convolution operation. So some of these things are really quite general. But I'm also going to talk about another difference that also helps us scale these things up higher and higher. Personally, I'm fairly agnostic on whose architecture is the best. One of the coolest things about working in this area right now is every 3 or 6 months, there's another model. That's amazing. It means that like with exactly the same training data set, trying to do the science, every 6 months, the test set predictions get better for no other reason than someone comes up with a better training strategy or another architecture. That's super, super, super fun. I don't know what's going to happen after Equiformer V2. I think there are people in this room developing stuff, and I've heard rumblings that there are next things coming. I don't know what it's going to be. I'm open to creative suggestions. Whatever it is, I think the community will benefit. Yeah, of course. Yep.
When I look at these as someone who works in condensed-based systems, like those errors for MD would be like totally intolerable.
100%. This is wild. Like 0.8 EV is like so bad that you should be asking real questions.
Yeah, because like KT, for the systems that we look at is 25 millielectron volts.
100%. Okay, so there's a couple of things going on here. This is really a great question. So first of all, when we started this project and all the models were at 0.8, like in all honesty, we were a little bit worried because like 0.8 is not anywhere close to being useful, and we were sort of worried that like we had bitten off more than we could chew, or like 500 million hours of compute was not enough and we needed another factor of 100. Like these were real things that went through our mind and made us quite nervous. we're asking these models to generalize to new surfaces and new molecules that the model has never seen before. And in many cases, for example, one of the validation and test splits is a combination of elements that's never been seen before. So you've seen like nickel-copper alloys and copper-platinum alloys, but you've never seen nickel-platinum alloys. That is a pretty hard extrapolation task. And that also gets to like, when we started this project 5 years ago, I would go around and give talks on like the stuff we were doing, and people were pretty skeptical. They said things like, look, you're always going to be doing an active learning small data sort of thing to fit the potential you need for the system that you want. And that's a really, really good strategy if you don't have a base potential and you need to start from scratch. But we wanted to see how far we could push this. In actuality, and again, going back to your question, these tend to be a little bit worse than they actually are in practice. And so if you only do metals, so things that don't have a really interesting electronic structure, and you also filter for things where the surface is not reconstructing or moving during the simulation, so those are also, there's some ambiguity there on what the right way to reference an energy is. These numbers are more like 0.15 or 0.2 after you do that filtering. And also in practice, the absolute energy is usually not the most important. If you want to use this thing for the relative energy, that's often what you actually care about, and the numbers look even better for that too. And I'm also going to touch on that at the end, because it was also very surprising to me that any model with a 0.3 eV MAE was at all useful for chemistry, because that number is so big that I agree it's scary. Yeah, other questions? Yeah.
This is for all the atoms. This is per unit cell. I think that the machine learning force field people in condensed phase typically divide by the number of atoms.
Yeah.
I would say
for surface chemistry, it's a little ambiguous. So like we could divide by all the atoms, but like we're subtracting out the bare slab. Should we divide by the number of adsorbate atoms? Should we divide by the entire system?
But
Like,
I mean, if I take like one of our water molecules and multiply by 64, like it's still,
yeah, it's still very different. Yeah. Another thing to remember is people tend to come at this from a what does a classical potential sort of do? But in order to solve this problem, you're actually forming and breaking bonds constantly. So this is an extremely reactive potential. And so like all the numbers are worse if you actually need something that breaks bonds for arbitrary metals. So that's also why there's a little bit of a difference in the community. If you're just doing water and you're not breaking bonds, then you can do things that are way more, or just shuttling protons or whatever you can fit for what you want. I know. Yeah. The closest sort of kind of type binding, but even those don't, yeah. I wish that there was one, but we should chat afterwards. Okay, so the takeaway from this is there's steady progress, and this happens by involving the machine learning community, and you get a bunch of ancillary benefits by the entire community getting involved and contributing to these new architectures. So just to give you a sense of qualitatively what's happened, on the left are 4 random relaxations from DFT. This was an example system when we, example model when we started. Schnet was released in 2017. We trained this model afterwards. Like, it's not going crazy, but it's also not doing the right thing. It's moving around in a way that the DFT is not doing. And if you look at some of the newer models like ESEN on the right-hand side here, and just watch compared to the DFT, to my trained eye, that's pretty darn good. It's not perfect, right? But it's way closer than where we started, and so that's also been super exciting. Okay, this has also been interesting enough that we felt comfortable actually putting this up as a demo. So this is a website, open-catalyst.metademolab.com. I'll post a link also at the end. You can go, you can specify your favorite material from the materials project. You can specify the facet that you're interested in. It will go and do adsorbate enumeration for you and try and place it. These are things that are super manual, like order weeks or months for a trained catalysis PhD student to do if you're doing everything with DFT. This is Abhishek selecting the adsorbate. He runs, it goes ahead and does the enumeration. Great, these are all different possibilities. This is often a global optimization that we're doing of an adsorbate sitting on a surface. He just clicked run. There's a bunch of GPUs on AWS backing this thing. It usually takes a couple of minutes if you want to go and play around with it. And then things should show up here, and it will be little ML relaxations, which you can actually use to say what is the best configuration on a surface, or you can also use to directly do things like reaction networks. Also, quite interestingly, Lars Grabau from the University of Houston used this as part of a graduate course in catalysis for the first time this spring. So he actually had students using this as part of a final project to do catalyst screening. Okay. Last slide before I start talking about problems and things that I wish people in this room would solve. So anyone who wants to use these models, we've collected a bunch of different architectures. There's an open repo. We rebranded to FairChem because we're now not just doing catalysis, but also things like direct air capture and other domains. There's a website. This is a little snapshot. We have, it's much easier to install now. It's all MIT licensed. We have some educational resources. Larry Zitnik did a little why model atoms for climate YouTube series for people in the machine learning and computer science community who weren't quite sure how to contribute. There's a inference service that I just showed you. There's all these different data sets that anyone can just download. And then you can also download directly the trained checkpoints as well for whatever use you want to do afterwards. Fine tuning, transfer learning, whatever. There's a lot of opportunities there. Okay, so switching gears a little bit. There have been a couple of things that I've seen where I was a little skeptical when we started this project that this was going to solve a lot of problems, but I've been getting more and more excited. So two things that we do in catalysis. One, we try and find the best adsorbate configuration on a surface. So usually there's some sort of corrugated potential. You move this thing around, and it is, again, on some poor graduate student to basically do this by hand. You do this 15 times. You come up with little pictures like this. You take it to your PhD supervisor. He looks at it and says, oh, but you didn't try this other one. And you go run another couple calculations and then repeat. That is literally the state of the art for what we're competing against because these simulations are so expensive. The other thing that's really important in catalysis is what is the transition state, the barrier between initial state and final state, because we need that for kinetics. Catalysis is the rate at which we are breaking things, and we're trying to make that as fast as possible. And so we also want models that work in between. And Rafa also touched on this too, right? There's been a ton of work on relaxations, but really we want kinetics at the same time. So starting with the first one, basically the heuristic process that most people use looks something like this. You select a little molecule that you want to put on your surface and the surface that you're interested in. You enumerate a whole bunch of initial configurations, either with some heuristic placement strategy or some random placement strategy, but you can also choose whatever your favorite global optimization method is and do that too. You do a bunch of relaxations, you filter, and the best one you call the adsorption energy. You also have to make sure that you don't do something crazy like breaking the little molecule apart if you have a really bad guess. This is, again, just part of the process of saying what is an adsorption energy. If you take one of these pre-trained models and you use it to relax all of the configurations on a surface, a bunch of candidate configurations, and then you run a really fast DFT single point just to verify the energy at the relaxed configuration, the results are starting to look really good. So SCN MD large, so these are DFT, the best ones according to DFT. So that's this column. Over here, these numbers are quite close. This one is actually a little bit better. These are all DFT values. Qualitatively, most of these are in the same spot. If you use this algorithm to not just say what is the best configuration, but maybe like what are the best 5 on a surface, you can do even better. And what this maps down to is something like a 1000x speed up because the ML model is working well enough, zero shot on a new adsorbate on a new surface, that it can tell you what is the best configuration, and it can tell you what is a relaxed configuration, so you don't need to do another relaxation, you just do a single point evaluation. This was quite surprising to me. And I think this is also interesting because it gets to Grant's question as well of like, why is the model working if the values are 0.2? Like it should not be usable if you just like naively think about that as an energy estimate. Part of the trick here is if you sort of take like a trust but verify sort of approach to these things and you use it to go as far as you can and then you just validate with DFT, you can also do a lot better, right? As long as you get the right configuration, you're pretty close. And then you just validate with the energy at the very end. And then if there's any systematic offset or whatever, you can fix that. Okay, so that's one. Maybe even more exciting, and again, touching on things that Rafa mentioned this morning, one of the summer interns, Brooke, who was also a PhD student who was working with me and is now working with John Kitchen doing the same things. Last summer, she came to FAIR, and she was working on this intern project where we assumed what we were going to have to do is we had this big catalyst data set, and it was only relaxations. So as Rafa said, these things had only seen little local minima. And the assumption was we were going to build another data set for transition states. We were going to like systematically like place things on surface, blow up bonds, make these things work, do a ton of DFT, add it to the training data set, and then there'd be another generation of training data and models in order to make these things work for transition states. So the first thing that she did was she built this new data set that's also online now, OC20neb. It's about 1,000 nudged elastic band transition state calculations across a very wide representative set of very weird looking catalyst surfaces and very weird bond breaking, but like really, really quite random, not like just simple little toy reactions. And the goal of this validation data set was basically to be the precursor to the next training data set that we needed to solve the problem, and also help us identify whether or not we were actually solving the problem. Like if we had some method that claimed that it could do transition states, we needed a validation so that we knew if we were actually solving the problem or not, right? That's the first step whenever you come up with one of these cool new ML methods, is to say, how are you going to be sure that the thing is not overfitting and is solving a real problem? So really interestingly, if you take one of the pre-trained potentials that has only ever seen relaxations and you use them naively in a nudged elastic band calculation, you just basically try and do the transition state finding calculation that you wish you were going to do, about 70% of the time, the energy that you get with the model is within about 0.1 EV of the actual answer if you had done the whole thing brute force with DFT. So that's like a 2,000-fold speed up, and it gets you pretty close. If you're willing to do a little single point on the initial and the intermediate state and the final state, obviously you're doing a little bit of DFT now, you're validating things, so that takes a little bit of computational cost. The number goes up to about 85%, and now we're down to about 100-fold. If you do a little relaxation on the initial and final point, or you're willing to do a final neb relaxation, you can still get a pretty good speed up, but then you get the rest of the way. And frankly, this was quite surprising to us. Again, we aren't retraining our model at all. The only thing we can think of is one, over the course of these things moving from one site to another in catalyst surface, you are breaking and forming bonds. So it's not like these things have never seen a bond break before. The other thing is, in OC20, sometimes we do a bad job of guessing an initial configuration. And like I said, one of the things you have to watch out for here is you place a little molecule on a surface and it breaks apart right away. That's also a situation where like we've probably seen some bond breaking events where like we didn't mean to, but like it's part of the data set and we can train a potential on it. But this is quite exciting. And so we're also putting this into production now, trying to do reaction networks and other things. If you go and you look at this paper, there are two little toy cases. Both are published papers. One was a ACS catalysis paper where someone had spent a ton of time doing reaction networks for ammonia decomposition. Brooke was able to get exactly the same answers, much, much, much faster, in some cases better. The other was a reaction network project that I had worked on as a postdoc, spent a ton of time trying to find the right pathway. Brooke was also able to show that that works better. So as one example there, yeah, go for it. Yeah, it's in the paper of like different types of like, is it the reaction or is it the type of surface? Is it like really far from it or, yeah. Yep. And to make this a little bit more complicated, like even when you're using the ground truth DFT, like the nudge elastic band method is not like a really well-posed numerical optimization. It has its own annoyances. So anyone who does those by hand like has their own set of tips and tricks. So frankly, like probably a lot of this 5% or 10% is just the right person with the right tricks probably could have gotten it to converge. But if you naively just choose one set of settings and throw it at it, like it's not perfectly converged. Yeah. Yeah, these are all great questions. So as one example of how this can work, a really common thing in computational catalysis is you want the activation energies. So that is the barrier from the initial to the final state. This is the thing that goes into the rate law. That's what you want in your reaction network. But it is by far the most expensive thing you can do. And reaction energies are easier to compute. So what people do instead is they say, we're going to plot all the data. On the x-axis is the reaction energy. On the y-axis is the activation energy. Usually there's something like a linear form of that basically says, as I move this thing up, If this thing is halfway in between, it should also go up. If I move the final state down, the intermediate point should also go down a little bit. That's basically what these BEP relations are saying, these linear scaling relations. But essentially, computational catalysis reaction network discovery is built on a linear relationship between the reaction energy and the activation energy. Like, there's a lot of scatter there. It's not beautiful, but when you go and you look at your favorite computational catalysis screening study, that is what is state of the art inside of these things to say what is the best catalyst. If we do the same thing with our new method, basically using this to find the best point and then doing a single point of DFT, we can basically do much, much, much better. In some cases, even better than we would have gotten otherwise. And so I'm not going to claim that this has solved all the problems, but like compared to where the field was a couple of years ago, I think we're at an inflection point where all of a sudden transition state energies and kinetics can now be part of a routine catalyst discovery process. So I'm really excited about this, and we're trying to think about how to apply this to other more interesting outside of the box catalyst discovery efforts. One final example where we've seen some interesting generalization, and this again gets to the assumption about whether or not, and we've had a lot of discussion already, every time we move to a new material system, whether or not we need more training data to cover that space. Everything in OC20 is a intermetallic. That means that it's an ordered inorganic material. There is no disorder, there's no solid solution, there's no random swaps in that lattice. And they're only like mostly 2 or 3 elements, binary and ternary systems, with a couple of cases of quaternary. This is basically the materials project doesn't have very many multi-component systems. So really interestingly, if you take these models that were trained on these intermetallics and you apply them to high entropy alloys where you have 5 or 6 components, and they're a solid solution, so you can do whatever swaps you want, we can get pretty good zero-shot performance there too. There's a little systematic offset that you have to fix, so everything is a little high or a little low, but afterwards it works quite well. And so this was another case where like implicitly I was making an assumption that we were going to need yet another data on solid solution materials in order to fill that space of catalysis, but I don't think we actually need that now. It seems like the models have already learned enough in their representation that a solid solution is the same as an intermetallic, which is also fascinating, right? It gets to like an assumption on what sort of regime we're going to be if we're always collecting more data and building the next data set, or if these things are learning something fundamental. Yeah. Yeah, of course.
Which is about transferability across temperature. So
Yeah.
if I understand correctly, these are all like 0 temperature nudged elastic band. It's on the
Yes.
best energy surface.
Yep.
And like probably most of what you're looking at here is dominated by enthalpic parts of the reaction, right? But if you had something where there's like a lot of entropy and you need finite temperature effects, do you?
Short answer is I can't say for sure until we have a validation set of like free energy calculations or something else like vibrational calculations and a quasi-harmonic or something to like say whether or not the model can capture those things accurately.
But are there things that you've done at finite temperature that you can?
We've been trying to do things, but we don't have like a validation data set where we can say like, yes, we definitely feel comfortable in doing that. But like we can run these things and get vibrational modes, and a lot of the numbers seem like they look halfway reasonable. The next thing I'm going to talk about, some of the things that we do in order to make these things scale, make it a little bit harder to run dynamics, and not impossible, but just you need to be a little careful. And so that's another thing that we've been thinking about. Yeah. Any other questions? Okay. So another thing that's been touched on in a bunch of these talks has been the role of inductive biases and which ones are helpful or not. And I think this is a really interesting discussion because from my perspective a few years ago, it was basically assumed that the right thing to do was always to throw as much inductive biases as possible at the problem. And that was the right approach. It's not surprising, we're all physicists and chemists, like that feels like the right thing to do. We were all trained to do the right thing and include as much physics as possible. But as these data sets get larger and you work with people outside of the community who have spent a lot of time engineering these models to work well and train fast and scale, then I think we should start to rethink some of these. And so it's really interesting to see these conversations. I don't know where this is going to fall, but we're seeing similar things. So from my perspective, this is a way oversimplified picture. Where we want to be, we want as much inductive biases as possible, all the symmetries, physical priors, conservation laws, everything, like throw it all. If we know it's true, it should be true. And we want our models to work really fast, train easily. You throw them on a computer, you get to a local minima, that thing is useful. you want it to just work. So the faster you can make these things and the more biases, I am convinced if you can do both of those really well, probably you will increase the performance. And by performance, I mean something like outer domain generalization or whatever you want to call it. But like, there's all sorts of ways you can define that. And often we have a candidate model. We're trying to figure out what is the right thing to do. Someone comes to us with a model that they think works on a small data set, and then we say, what should we do for our large catalyst data sets to improve? And one strategy is you incorporate more biases. You say the representation was not good enough. We're missing something like GemNet. Angles are not good enough. You need dihedrals. Let's go ahead and throw dihedrals in and see if it improves performance. That's a valid strategy. Another strategy you can take is scale up the model. So throw more layers at it, make it deeper, change the normalization, play with other things. That's also a valid strategy. Both can also happen at the same time. But the thing that we also have to be worried about, and other people have mentioned, is that sometimes if the benefit that you get from making the model way bigger or way faster is offset by whatever you lose by removing an inductive bias, you can actually work better on some of these outer domain generalization tasks. And it's probably not going to be all the time, but for some of the tasks that we care about, that might be true. And conversely, sometimes you think you're doing the right thing, and you're including something that you're pretty sure should be from the real system. But because it makes it slower or harder to converge, as Aditya was talking about, you can actually make the problem worse, and you can take a step backwards. Where we actually want to be is in the upper right-hand corner. I mention this because the team I'm on, I work with two really talented machine learning people, Matt Utendahl and Larry Zitnik. Both of them come from a computer vision background. It's one of the really fun things about working at FAIR is to work with these other people with a different background working on these problems. And in the computer vision community, when you look at how people apply CNNs, it is really common to have models that are translationally invariant, and then scale invariance and rotation invariance or equivariance or whatever you want to do depending on your features. These are usually things that are you can do if you have a fancy model. You can also do through data augmentation. But a lot of models just stick with the simple one and then learn these other two through data augmentation because the cost of implementing these things is so high, or something else happens with the training dynamics that it actually becomes harder to scale the system up. And so working with people like that, they will bring these own ideas on how we should try and improve performance. And so I've tried to keep a very open mind. So in that vein, the method that everyone's talked about so far, and Aditi gave a really nice explanation on how to do these gradients and the loss functions. You do a forward pass through your model, you predict an energy, you do a backward pass for derivatives with respect to the atomic positions, you get your forces. And then a typical loss function looks something like this. There's a term for the energy, and there's a term for the forces. And then you throw this into your favorite optimizer, and you run, and you hope that it eventually gives you the right answer. This is good because you get energy conservation by construction. You have a guarantee. But it has a drawback of you just put a gradient inside of your loss function. And that has two problems. One is this thing is now like just about as expensive or sometimes twice as expensive in the backward pass just to get this thing as doing the forward. And then on top of that, you have a problem that if you then take a derivative of this with respect to all the weights, your model has to be very, very stable. You have to really worry about numerical imprecision and normalization and everything else. And anyone who has tried to take a double derivative through one of these really, really deep systems, like, understands how many little weird edge cases you can hit and how it can make your life harder. And so these are things you have to deal with when you try and scale these models up. So a very naive thing that you can do, sorry, before I go on, if you just do validation force as you train this thing, I picked a model that Abhishek and our group trained. I chose Pain not because it was the fanciest, but because it wasn't our model. It was just a reference implementation that everyone agreed worked fairly well and was a reasonable paper. You get a validation force that is about 0.04 on OC20 after about 20 epochs. Okay, so a naive thing that you can do is you say, I'm not actually going to take any gradients. I am just going to tell my model, you are now supposed to predict an energy, and there's going to be a separate head that is supposed to predict a vector that is the force vector. And I am going to train this thing, perhaps with augmentation, for long enough that eventually I hope that this thing looks a lot like the gradient of the energy. but I am not going to strictly enforce that in either the loss function or in the way that I constructed the model. And then the loss function changes a little bit. Now there's just a prediction from ahead that should match the force that we're seeing rather than saying the gradient should work. So again, not surprisingly, this might make things a little bit better when it comes time to train. You lose energy conservation, which is a little scary, especially when you start running microdynamics or other things. And as a community, we're really, really focused on energy conservation as like the #1 thing we all check for. But it becomes very fast and the training gets better. And so this is fascinating, right? Like when we look at the training dynamics now for these direct force predictions, there's a little bit of wiggle right here. This is probably just noise. If we repeated it, we'd probably get similar results. But the final validation forces are lower than we would have if we were doing the right thing with gradient-based forces. And it trains quite a bit faster. If we stopped at the same point, we could get results that are way better than if we tried to converge the one where we're doing the right thing with gradients. So that's really interesting. If we do the same thing for the energy, and remember the energy is not actually seeing anything from the forces now, except for the forces are being used to help the representation on the nodes, we also get better results using the direct force prediction. And so as a community, this is very surprising and also raises questions of, is it better to have energy conservation or is it better to be more accurate? Like there are real trade-offs here when you train on these big data sets of you are going to get worse results on the thing that you care about, the energy, by including these gradients naively.
Is it like the same distribution, you just split the training and validation, or is it out of distribution?
In this case, it was validation, so it was in distribution. But we also see similar results on way things out of distribution. So new catalysts that we've never seen before, new adsorbates that we've never seen before. The best models we've trained are with this direct approach. Yeah.
What are the consequences for stability?
These are good questions. We've mainly focused on local relaxations and transition states and other things. We can throw it into a little MD integrator. It's not so clear to me exactly what instabilities we see are related to step size or just sharp surfaces versus anything else. In practice, like it does look like the gradient. It's not like a wild difference. It's not like this thing is like pointing off in a completely different direction, but it's also not like exactly the thing that you would have gotten if you had said, what is the gradient? But this is something that we are actively working on right now. And Rafa also mentioned that forces are not enough paper. I really like that one. Shang Fu just joined our group. And so I don't know exactly what he's going to work on, but I hope he solves the problem. No pressure, Shang.
Those two approaches together, like do the direct force and then afterwards do the gradient based, like having initialized it in a sense?
Yeah, I think that's a great idea. So yeah, I'll go to that in a second. We've seen some hints. Nobody has like sat down and really tried that strategy, but it feels like a very reasonable one. You have like a pre-training thing where you try and get it as close as possible, and then at the end you turn it on. One thing that you might lose is there's probably a lot of information in that in the force head. Like it's seen way more targets than the energy one. And so there's probably a little bit of a risk that like a lot of what the model was learning was in the forces, and you lose that as soon as you then turn on gradients with respect to energy. But I believe it's a reasonable strategy. People are trying that. I don't have any like amazing results to show right now, but I think there's all sorts of ideas. Yeah.
You're probably not doing one-to-one weighting between the energies and forces in your loss function, right?
We are not. I forget what the magic number is, but yeah, if you look in the configs, you can see what the loss function weighting is. Yeah.
I know. So in the diffusion modeling world, it's like this question: oh, you can treat them as energy-based models, treat them conservatively. Yeah. There was this like workshop paper a while ago where they're looking at if you do a harmonic parameters. Like part of the problem is that if you do the gradients of a scalar neural network, you have to express the forces in like the basis of the input features. Whereas if you kind of if you have them predict these forces, and then you said I had this like you express your energy as like some like harmonic deviation from of the coordinates like from those forces, it like makes it more expressive. Anyway, in this case, they found that like the kind of perceived gap between training conservatively versus not like goes away. I was just curious if you've seen folks do like play this game of kind of it's essentially like skip connections of.
Yeah, I don't think we've tried a lot of random experiments while developing our own models. I haven't seen as many from outside of our group, but like I think there's probably a ton of things that we could try there. And so I really want to see other people play around with this and maybe even more importantly, tell us what we should be doing differently or a better training strategy. Aditi talked about all sorts of ways that we can do better training here. I think there's an opportunity. Yeah. So I just wanted to touch on one of Aditi's examples. I was pretty sure that she was going to talk about that paper. So I don't think this is like as surprising as it feels at first at face value. So in the example that she showed, you are adding a soft constraint. This is the PDE that you know is true, is ground truth. The thing has to solve. That's definitely the right thing to do. And you're putting it in the loss function, and you're saying, I'm going to enforce this thing by ramping up lambda and making it sufficiently large that this thing has to learn the right physics and it does the right thing. And Aditi has pointed out very nicely that when you do this, especially if beta is large, but also in other cases, if these gradients are big, you can make the problem worse by making the surface really spiky and have all sorts of other problems that come out of this. And that makes it hard to get the best possible model. And if you look at the loss function that we are applying inside of our training for most of these neural network potentials, this looks pretty darn close, right? We are evaluating a gradient of our model and trying to set it equal to something else that we think is true. And so I think it's quite reasonable to assume that probably there's weird things going on in the loss function as well, as we're trying to train a model from scratch while pinning the gradients. And I think this also gets to your point of maybe we can do this without the pinning first, so we have a very smooth loss function and we do we go as far as we can, and then maybe afterwards we end up in a really good local minimum. I think there's probably a correspondence here between strategies that work in the PDE space and also what happens here, because I think it's sort of fundamentally the same thing in both cases. Okay, so what do I want to see? More ways to include all the biases we care about and make things super fast. If you have a fancy architecture that includes some fancy representation, we're happy to work with you. That'll be super cool. Also, as Jennifer mentioned, another reasonable strategy is you train fast by relaxing biases and then you enforce later. Very reasonable strategy. I feel like it should work. I just don't have any data to show that it does yet. One thing we've told a lot of people, if you can show that some cool new training method you have works on a small subset of our data, so like 2 million is actually pretty approachable for most academic research groups. It's about 1% of the entire data set. If you come to us with some interesting validation and test results, we're happy to help you scale up. That's how like Equiformer V2 came about. There was a summer intern who was scaling that thing. GemNet OC was the same way. GemNet looked cool. We worked with them. They did an internship. We scaled up. We're happy to help you in that process if the only thing limiting you is the number of GPUs that you have. Okay. Any other questions on this before I move on? Hopefully this also leads to a really interesting panel discussion afterwards. Yeah.
Do you know how close you are to conserving energy?
Short answer, no. We could just evaluate, like, add a bunch of representative configurations. What is the divergence, and say how close to zero are we? And then hope that we can sample enough that it is representative of how we use it in validation and test. One of the reasons why the answer is no is if you really want that gradient to be well posed, you really have to be, again, very careful with the normalizations that you use and the quantization and everything else. So like another thing I didn't talk about is if you want these models to train fast, another strategy you can use is mixed precision, right? The chemistry community is like very much like double precision or nothing. Like we just want everything to be as many floating point decimals as possible. It's very reasonable if you're trying to get the 15th decimal place correct. But if you're training these large models and you want it to go fast, you can turn on automatic mixed precision in PyTorch and let this thing run. And so that's another thing that makes these things a little bit harder. So we could evaluate some of the gradients, and it can be difficult. And so then it's a little bit hard to know, like, what is the ground truth? Yeah. Does that make sense?
It's a lot harder than computer vision, where like I can just rotate the image and see the data augmentation preserves equivariance or invariance.
Yeah, because you actually want to calculate the divergence of the energy and say, is that thing actually valid or not? Right. And so that divergence operation also needs to be well posed for the model. And like There's nothing stopping you from doing it. You can like ramp up the precision and then fix whatever normalization things you have. But this is like a cost that comes into the software engineering and the scaling of these things. Yeah. We should chat afterwards too. Yeah. Okay. So switching gears just a little bit. One final thing I wanted to touch on, and again, getting to Grant's questions of why are these models useful? Because again, they don't look perfect, and they. No, I know. They're going to think you were the plant, right? I paid you something in order to ask that question, and now I just get to say that's why I'm doing this. You didn't see, but like in the middle of the talk, I exited out and I added 15 slides just to address that. Okay, so in the chemistry community, what we actually care about most of the time is an energy difference. So a formation energy is the energy of a inorganic material that we make relative to two pure component states. And adsorption energy is the relative energy of a small molecule sitting on a surface relative maybe to those same molecules in the gas phase with some nuance on exactly how you reference that thing. But we're normally using these models to answer questions about is one thing better or worse than another, or what is the energy relative to something else. So a useful question is, if I have two different configurations on a surface, which one is a better configuration? That's like that adsorb ML sort of task I was talking about. I want to find the best configuration on a surface, and I want to find the lowest energy one. That is useful. I can think of a use for it. It's something that the catalysis people do. It is a reasonable question to ask. A less useful one is to pick two other random examples. What is the energy of this relative to the energy of this? I have no idea why I would be asking that question. It's probably going to be hard. The number is going to be sort of weird. Even from a DFT perspective, and I'm going to talk about that in a second, DFT also struggles when two things are very different. And so some of these questions are not even well posed at the ground state level. Okay, so the computational chemistry community has known that this was important for a while. And so one example of this is inside of these DFT codes, there's something called the exchange correlation functional. When you ask people about how they, what method they're using, that's one of the things that they will respond with PBE or RPBE or some hybrid or whatever. If we knew the right answer, we would just use it, but we don't know the right answer, so all we have is approximations. And those approximations are fit on a very, very, very small number of experimental data points. In computational catalysis, the number of data points is like order 60 adsorption energies and 10 transition state energies. Those 70 data points influence how you fit that exchange correlation functional. And if you had a different 70 data points, you would get a different answer. So there's this functional called Beef van der Waals Bayesian error estimation functional with the van der Waals correction. Basically, it is an ensemble of functionals that you could have gotten if you had fit to different experimental data points among that 70, right? Just saying that like you chose 70 random ones. If this was a different world and your experimental collaborator had done 5 other random ones, you might have gotten a different exchange correlation functional. And so this looks like things like the enhancement factor could be different, and these are all different functionals that you could get. And so one nice thing about this approach is that it allows you to say, how well posed is a particularly energy difference am I interested in? So one example of this, AJ Medford at Georgia Tech did this as a PhD student. If you ask, what is the uncertainty in the adsorption energy for nitrogen on an iron surface, you have a certain error bar. And if you do the same thing for ruthenium, you also have a certain error bar. So far, so good. This is just uncertainty propagation. We have an ensemble of different models. We just push the whole thing through, look at the error bars. If you propagate that thing through a microkinetic model, say, okay, given those and transition state calculations, what is actually the rate? That's on the y-axis. This is the thing we actually care about. Is iron better than ruthenium for this chemistry? The error bars here are a little bit scary because they're actually overlapping for ruthenium and iron. I would say, according to this sort of analysis, we actually don't know, is ruthenium any better or worse than iron at a statistically significant level. Like, we should be worried when these things are overlapping. Should make us a little bit nervous. If you reframe the question and you say, what is the rate relative to what you see of iron, and what is the adsorption energy of nitrogen relative to iron, and ask your DFT functional to do that, and you do it 2,000 times for all of these different examples, you can show that this is actually a really well-posed question. The functional, it doesn't know the actual energy of nitrogen and iron perfectly, but what it is very convinced of is ruthenium is way weaker than iron, and the rate of ruthenium is way higher than iron. Again, the absolute ones are a little bit sketchy. We normalize by the iron, but the relative ones we actually do know. And I'm mentioning this because the way that we're actually going to use these models is an energy difference, and so we want our models to work that way, but that's not how we train our models. Instead, we just train our models on give me the absolute adsorption energy. So if we want to make the distribution as tight as possible, we want to reduce the error in our predictions. This is me going to Wikipedia and just pulling our favorite propagation of errors from intro chem class or intro stats or whatever. The definition for a random variable A minus B is the standard deviation of the resulting one, if we assume Gaussian, is the standard deviation of A squared, sorry, this should be B, plus the standard deviation of B squared minus twice the correlation times the standard deviation of each. So far, so good. We have two random variables that we're trying to subtract, and we're trying to say, is it narrow or broad compared to that? So there's two strategies, right? If we want this green thing to be as tight as possible, the easiest one is you just make sigma A and sigma B really, really small, and the problem goes away. That is saying, if I make my ML potential infinitely accurate, I don't really have a problem, right? Eventually, the things will collapse, and I will be able to resolve the energy difference. The other thing that you could do is you could say it would be really nice if our ML potentials actually just were correlated for the energy differences that we cared about. And if it was wrong in the right way for the two things that I'm trying to get the energy difference of, I can still get the right answer. So far, so good? Make sense? Okay. So we were asking questions like, why are these models working for things like adsorb-ML for two different configurations on a surface? So a couple of the ways that we can use these models, we can say for the same adsorbate, let's change the catalyst, or the same catalyst, let's change the adsorbate, or the same adsorbate sitting on a surface, let's change just where it sits on the surface. And in this OC20 dense data set, basically lots and lots of different adsorbate configurations on these surfaces, if we just naively look at all of the pairwise energy differences that we could have in our system, we're changing two at the same time about 94% of the time, and usually the energies are really big. And on the other extreme, if we are only looking at the relative energy configurations of two local minima on the surface that are already quite close in energy, then we don't have very many examples, and the energy differences are really small. And so if I want to say, is one better or worse than the other, I need to be quite accurate here. Okay. I told you that there was a magic DFT functional that can also allow you to ask the same question. So for beef, which is, again, just one fitted one, but at least it has an ensemble that we can look at, the standard deviation of the error distribution for all of the adsorption energies is about 0.38, and the average for the difference is about 0.42. And then if you go and you look at the average uncertainty, the average standard deviation for these different configurations, these numbers also decrease, sort of corresponding to what we were seeing here. So that says that beef is able to get more and more accurate for the cases that matter. You're looking at two really subtle differences. You shouldn't be so worried about the overall problems that beef has. Beef actually knows what is the relative energy of some of these. If you normalize by these numbers, what that says is you have about 40% cancellation of errors in the catalyst and adsorbate swap cases, and you get about like 75% on some of these more subtle ones. The functional is working much better than you would expect if you just naively said, how inaccurate is the model that you're using? Okay. So we can do the same thing with GNNs. Where is this going? Let's do the same thing with predictions from our favorite ML models. We're going to take a model that has a whole bunch of predictions for the adsorption energy, and we're going to do the same thing, but we're also going to do random pairs of energy differences. And then we're going to measure the standard deviation of the resulting distribution. And if that thing is lower than what we'd expect from naive Gaussian propagation, there was some sort of cancellation of errors. So if we look at these numbers, we are seeing that these numbers are going down compared to the ones over here, the overall average. And this becomes more clear if we normalize. So in these cases, for some of our latest models, we're seeing approximately the same cancellation of errors for some of these really subtle energy differences, which is really quite exciting. And what's also interesting is the amount of cancellation of errors that we're getting is different for these different generations of ML models. Like something about what happened going from SCHNET to GEMNET OC large, these things are now closer in whatever representation it's learned, and therefore we're getting more cancellation of errors. That's like a hard thing to prove. I would love to get some other ideas on like how to like rigorously show that. But like this is the best thing I could think of to say like the representation that is being learned is physically meaningful compared to the representations being used in DFT, where we're making the argument by what would these functionals do in similar situations. One thing that is a little bit scary though is if you notice when you change the catalyst or you change the adsorbate, we get basically no cancellation of errors, but DFT is getting quite a bit. There is some sort of correlation there. So I don't know what's wrong with how we're doing stuff in GEMNET OC large, but I would say that's a bit of a flag that the underlying DFT functional should be able to say what the energy differences are, and that's not happening in some of our latest models. One other thing that we can do is we can go and in these invariant models where there's a big vector that's invariant that we can look at distance in, we can compare the embedding similarity versus how much cancellation of errors we see. And again, what's super interesting is even within the same model, just by scaling it up, we get closer similarity for things where we're trying to do energy differences, and the error cancellation goes up. So again, this goes back to like something about what's happening in the representation that's being learned as we make these models bigger and bigger is helping us do the right thing when we use the models downstream. And that is a partial explanation for why these things are more useful than, again, if you just took them at face value and you said, what is the global energy difference? And the proposal and sort of the root of all this is I started this project with a PhD student at CMU. My hope was that we were going to do something like this, and then we were going to put something fancy in the loss function where we were only going to train on energy differences that we cared about, or we were going to change the way that we were training this thing, and then all of a sudden the models were going to get even better. All of our experiments failed. I don't know why. That's not to say it can't be done, but I think that this is very interesting because, again, the way that we're actually using the models is not the way that we're training them. So there is a discrepancy between what we want our models to do and the actual use case. So I really, really wish that someone would come along and tell us a better way of training these things so that when we actually use them, they would be more useful. Connor.
For those tests, were you doing like regression tasks on differences or like ranking loss functions?
Both. Yeah, exactly. Yeah, those were the two obvious ones that we were able to come up with. So there's all sorts of different ranking loss metrics that you can try. Again, it was a first-year PhD student. He was very motivated, but like he tried a bunch of things. That's not a proof that it won't work. It feels to me like it should work. It seems like if we're just fitting on average energies, that's probably not the only thing. But yeah, another situation where I wish someone would come along and do something fancy here to make things more useful.
Just as an FYI, there's like a minute for everything left.
Okay, we've had a bunch of questions. So yeah. So and we'll have a discussion. So this is also it. We can end there. Thank you. Lots of people. Feel free to follow up.
Time for questions. I just
Yeah, of course.
I didn't know that was coming.
No, yeah.
Maybe I can ask a question actually.
Yeah, great.
So you've been generating these large data sets, and there is this question of the level of theory. So you're making some inherent trade-offs that you might be able to generate more data, but that means it might be at a lower level of theory versus vice versa. Have you noticed any interesting patterns in the amount of data you generate versus the level of theory and how that affects outcome accuracies for downstream tasks?
Yeah, so the closest thing we've done, there's different levels of theory. There's also different numerical tolerances within the underlying DFT codes, like how well do you converge these things? And if you converge them farther, then hopefully the energies get closer to the actual one. If you did perfect convergence, you went out all the way in something like the cutoff in the energy or the number of K points or something like that. If you were just looking at total DFT energies, we would have a problem. because the overall energy changed quite a bit as you change those two things, and we did not perfectly converge those. One of the students working with John Kitchen, Kareem, also worked with Mohammed, and they went back and chose a subset of OC20 and really converged everything, sent the cutoffs out really far, increased all the K points, tried everything else they could to converge things. And the end result was the absolute energies change by a lot, but then when you do an adsorption energy, almost everything cancels and you get pretty much the same numbers. And so that was a case where like I was pretty convinced that we were going to have to release an update to the data set of like just a subset of the things needed to be more converged. But in actuality, this cancellation of errors idea is really powerful. You do the wrong thing twice and the difference cancels. For wildly different levels of theory, I don't know how many we would need. So like we've also thought about things like if we went from RPBE functional to pick your other favorite one, could we upgrade the whole thing with 1,000 data points or 10,000 or whatever the number is? I don't know. If you take one of these pre-trained potentials and then you fit on a smaller amount of data, they seem to work quite well. But it's hard to like prove exactly how much you would need or even what the right way to sample is. This postdoc who was working on that, Tian, is starting at the University of Alberta. I think this fall or next fall. He would also be a great person to chat with. He thought really deeply about a lot of those questions. Yeah.
One more question. Okay, in that case, thanks, Zack.